Hi. In the last video, I recorded a pre-introduction after having pulling that video down. And that was the result of a comment made by LS Fresnels on my video 79. It was a pretty significant comment. It actually caused me to stop and think a lot about the build and some of the poor design decisions I had made and whether or not I could actually recover from those. And there's several that I don't believe I can. So this video was partially recorded, and I'm going to use some of the footage that I've got where I can, and I'm going to be re-recording. Some of it may end up out of chronological sequence, so forgive me for that, please. But I want to take a moment and look at the comment and share with you some of the epiphanies I had as a result of what was said. And they were pretty significant. Now, most of this I knew, but I was so deep into the details, I could not see the specifics and perform my own root cause analysis. So I'll put the comment up on the screen, but the very simple question, which was a very good challenge, was, why do you really need a 4-cycle clock? That's a simple enough question, and I thought I had the answer to that question. But it was challenging me to take a step back and rethink that, which I did. I accepted that challenge. Specifically, after you do the synchronization parts related to the clock, which are only registers, which I knew, you really only have combinational circuits left, which again I knew, but I wasn't putting 2 and 2 together on that. So thankfully the question was raised and I was able to take a step back and think that. Now, that's actually a very valid point, is I was running into problems with timing and understanding timing and taking care of timing. My solution to those problems was incorrect in that I was adding more registers, more latches into the build in order to solve my timing problems, and that was going the wrong direction very clearly, which is what was driving me towards a 4-cycle clock. The next comment that struck out at me and hit me pretty hard was, by registers, I need all of them. And this is a partial comment, of course, but yes, I was adding registers. I was adding registers into the ALU so that I could manage the timing, and then creating more timing problems, thinking I'm solving timing problems. The last comment that stuck out at me, and this one hurt, if the processor instructions are too complex, you can split them into several micro-coded instructions, each taking 1 clock cycle. I have been trying to avoid this. Now, it was baked into the constant operations where I'm loading a constant into a register or adding a constant into something. But what hurt about that was I realized, like someone hit me with a sledgehammer, that I was avoiding multiple cycles per instructions at the cost of making every instruction a 4-cycle instruction. That's the wrong direction. And so I did take a step back, I did look at that, and I realized where my mistakes were, and they became very clear. My first realization was as I mentioned, I was adding latches into the circuits which required clock in order to manage timing problems when I should be removing clocks to manage timing problems. Make all that circuitry as combinational as possible unless I am latching a result specifically. One of those was the ALU results latch. Now, the ALU results latch is not bad in and of itself if it's part of the architecture to latch the result of an ALU operation and not store it back into the register. Well, that's not part of what I'm trying to do here, so it's incorrect to latch that result. The second realization was that the ALU really should be trivially simple to implement. It should not be the most complicated circuit on the build, and therefore should not cause me all the problems it's causing me. We'll get to that in the emulator here. The third realization was my general purpose register is flawed, and I'll go so far as to say fatally flawed. The design decisions I have made in building that register have driven my design decisions now, and they've been bad decisions on top of a bad decision. It's the only thing I've really committed to PCB twice, and there will be a third iteration of that. The fatal flaw related to that is over the load, increment, and decrement signals, and I never should have combined load with increment and decrement. And so we're going to come back and revisit that and try to straighten that out. But I'm going to do that in conjunction with the backplane because I do need to order another backplane because of power issues. And so we're going to start building up a new PCB order and get that off for manufacturing. Last, I realized it might have been a fundamental mistake not to extend the clock to perform the latches. Again, the clock is really the synchronization element that takes care of all of the data storage and basically pausing the process of the circuitry. By changing how I'm looking at this, I need to look at where things are going to be stored for a clock cycle or more and use the clock in order to manage that. Everything else, and this is what was the point that was made in the comment, everything else can happen in between those clock cycles. And the clock cycle is only there to mark the result of that. So I'm going to go back and address my control logic as well and put the clock cycle back into the actual mix there. I don't know that it's going to simplify the control logic so much, but it will simplify the build overall. Thank you, LS Fernels, for the comments. I do genuinely appreciate them. They're spot on. LS Fernels also has a second channel. It's probably the one that he's most active in at the moment, and that's at Relay Computer. I'll throw a link down on the bottom of the screen and a link in the description. He's building a computer out of relays. I recommend you go check it out. Okay, so for today I'm going to start modeling the ALU Adder in the emulator. Ultimately, what I want to be able to do is put something on ALU A, put something on ALU B, have the adder add those two numbers together and show the result. Now, I'm going to ignore the flags for the moment. That'll come once I get this settled. And we'll see how far we get with that. Let's get into it. Hi, I'm Adam. I'm still building a 16-bit computer from scratch. I'm no expert here. I make lots of mistakes. So many mistakes, I've actually had to reboot my computer build. I hope you will find my journey interesting, and I hope you will join me as I learn along the way. The first order of business here is to take care of my inputs, ALU A and ALU B, into the adder. Now, this is really just an extension of what I did in the prior video. I highly recommend, if you have not seen it, go check it out, video 80, where I went ahead and created a generic bus, made sure I could display its outputs and take direct input into that, which I knew I was going to need for this video. If I go and I select every other bit like I did in my test case, one of the ones that failed miserably on me, I can assert each of those out onto their respective buses. Each bus and each output operates independently. Right now, everything is driven from manual inputs on the screen. So the changes weren't really too intrusive. I did end up adding names to a couple of these components so that I could put a name on the screen so that it was easier to identify exactly what was going on. So my LEDs now accepts the name. My inputs, my dip switches now accept a name. And then for the computer, I added the two buses and the two bus drivers for the manual input. It was relatively easy then to take the code I had from the last video and extend that and make an ALU A and an ALU B along with their associated inputs. Of course, I had to allocate ALU A and ALU B. Really quick for transparency, in the line driver, the comment was incorrect, so I took a moment and corrected that. To get the ALU Adder operational, I needed to add two new ICs into the emulator. The first I'm not going to use right away, but it is a 74 HCLS, whichever you prefer, 74 HC540 inverting line driver. So what it does is it takes the inputs, it inverts them, and outputs inverted copies of what was put on the actual line driver to put out onto the bus. Now, this is very much a copy of the 74HC541 that I've done already. I just did some renames here in the header file. The actual implementation in the C++ file looks very much the same, with the exception of these 8 lines, where I am explicitly conditioning the line to invert. That way, if it is a Z, it still outputs a Z, high impedance. Otherwise, if it's high, then it outputs low, or if it's low, it outputs high. The other one I had to implement was the 74HC283. Now that's the one I'm actually going to use in the build. Again, the 283 is functionally equivalent to the 83 that I have in the breadboards at this point, but when I go to PCB, I'm going to be ordering the 283s in order to use those. The big difference between the 74HC283 and the 74LS83 is the pinouts. So in this one, I'm going to hang on to an A value, a B value, and a sum value, and I will maintain those internally. Otherwise, most of this looks the same. I have changes for carry in, the A inputs, the B inputs, each of which is going to call this update sum function. This is a private function that's going to handle the calculation of the values in the background. And then I have signals for each of the output bits that would be updated, the sum 0 through sum 3, and the carry out updated. That way I can notify anything downstream what has changed. Now the implementation here looks very similar to what we've done in the past. Everything is tied low, and then I've pre-calculated the output and set the values accordingly. So A is 0, B is 0, sum is 0. The carry in is taken directly off the pin. Got to trigger the first updates to make sure everything downstream of the IC is in good shape. And then I've got this update sum function. So I'm calculating A as a bitwise OR of each of the individual pins. I'm doing the same thing with B. And then I'm calculating the sum as A plus B plus, if the carry input is high, then 1. If it's low, then 0. Now, high impedance is going to come across as a 0 in this particular case. That may or may not be congruent with the way the real hardware works, and it may be logic family specific. In other words, HC may behave differently than LS. But everything should always have an input into these, and I'm going to make every effort to do that. If for some reason something happens to come across as high impedance or Z, I'll need to recall that and work that through. Let's take a moment and reorganize that so that it's accurate. Bit 0 is my new sum, bitwise ANDed with a 1 shifted to the left 0 bits. So I'm taking the least significant bit, and that's bit 0. The next bit up is bit 1, 2, 3, and 4. Bit 4 will ultimately become the carry bit for this particular adder. And so if something has changed, then I'm going to update the output pin and emit the appropriate signal. And this happens all the way down through the list, including carry out, which is bit 4, as I mentioned above. We'll test this IC emulation when I build out the ALU. So let me get the build out. I need to work from that from here on. Okay, so the ALU is going to be built basically up to about this point from here on up. And what I need to do is I need to go through and catalog where everything is going so I can actually capture that and put that into the emulator. Now the LEDs I've got and the line drivers that drive the LEDs for ALU bus A and ALU bus B, I'm not going to put the line drivers in the emulator, but the LEDs I've got. So my input here is a 74HCT541. I've got 2 of those, and that is an ALU, is this A or B? That's ALU B input buffer. I have 74HCT541, 2 of those up here. That's ALU A input buffer. I've got a 74AC86, which is used to select between these 541s and what will be 540s over here. I'm going to make a note of that. I may not add that right away. These are control signals. I'll come back around to those in a minute. Here I've got 74 LS83s. These are all 83s. And I'm going to replace those with HCs and 283s. Functionally equivalent. I keep repeating myself, but once again, I've got the outputs LEDs, which are going through a line driver. I'm not going to include this line driver, but this line driver is for the output of the adder out onto the internal ALU bus. Since I'm not latching anymore, this will end up being direct output out onto the main bus. And then the last thing I'm going to end with here is a latch. Yeah, this is one of the problem latches that is creating the need for the 4-cycle clock. I want to remove this. I'm not going to add it into the emulator, even though it's in hardware. Once I think I've got the emulator settled, I will come back and address hardware and update the ALU and breadboard. I have signals, ALU-B invert, carry select, ALU assert, and then I've got output enable. This is a little rough for me to write in this configuration, but this now gives me what I need so that I can pull this apart and start putting it into the emulator as an ALU adder, and then feed the components into the ALU itself. So there's going to be 2 components that I will add to the emulator as a result of this, and I have to split these components up into which is which. Okay, I think I was able to find all the video I'm going to be able to keep. I think I've got everything dialed in ahead of this. So I'm back in real time after all the realizations that I had. This is what I ended up with. I still have the 4-phase clock here. I've got the oscillator, but I've got the clock run modes here still associated with the 4-phase clock. I do need to clean those up. I've got my ALU-A input, my ALU-B input. I can turn them both on so that they're both asserting. I'll even go so far as to stop the clock. Right now, everything's being asserted out onto the main bus in the emulator. Now, as I turn stuff on, you can see that the output here is being updated. And as I go back and process my way through this one test scenario I had so much trouble with in hardware, you can see it works here in the emulator. Now again, I'm not clocking anything because this is all combinational logic. Okay, so how did I do all of this? Well, I created an adder, and just like on the breadboards, I've got 5 74 283 ICs in here. Again, this is to calculate 16 bits, but I've got 20 bits wide worth of adder. Why again did I do this? I did this because I want visibility to that carry bit into the last bit so that I can compare the carry in and the carry out of that last bit's operation to see if I've got an overflow. I also have a line driver. I've called it a bus driver, and I've got all 16 bits buried in this one component here. But this is what's going to drive out onto the main bus. And I'm passing the main bus in as part of the constructor, so that when I build this driver object, it takes care of the connections to the main bus. So I allocate my 283s, I allocate my bus driver, I set some object names. I do this primarily for debugging. Any of the unused bits get set low or high. And then I start making connections. And that is that off the ALU-A, I need to connect to the adders, the appropriate bits. And again, I've got 16 bits spread across 5 different ICs. So there's 1 unused bit on the lowest and 3 unused bit on the highest. And again, those are tied alternating low and high. You can see it here with the least significant bit, such that the carry input is going to guarantee to propagate its way up the food chain to the actual first bit. And same thing here at the end. I've got low and high, so low is added to high. That propagates up whatever carry all the way out the other end of that IC. Take a look at video 60 for more information on this. I go into a little bit more detail there. After I connect up ALU-A, I connect up ALU-B using the same methodology. I create the carry signals that carry from one adder to the next. And finally, I connect all of my outputs up to the line drivers so that they can be asserted out onto the bus. The carry itself needs to be connected to the signal for the carry output updated. And then I set my carry flag in and my carry flag and my output enables associated with the line drivers and do my first updates. Now the rest of this is really what you've seen before, making sure that the initial state of the emulator is proper. In the ALU itself, I have the buffers that I identified for ALU-A and ALU-B. Now ALU-B is going to also have eventually a 74540 IC, or a pair of them more specifically, and that's going to be for doing inversion. We'll get to that here when we start working on subtraction here. But again, my constructor is taking several of these different objects, and so you've got the ALU-A bus, the ALU-B bus, and the main bus. Now there is an oscillator that comes in here, and that is used. Well, I don't believe I need that anymore because I did have a temporary ALU or an internal ALU bus against which I needed the oscillator to perform the sanity checks. And I no longer need that oscillator object. This can go away, some real-time debugging. Rubber ducking helps. Okay, that's working like it should still. And finally, in the implementation of the ALU, I'm allocating the line drivers, I'm allocating the adder, getting that all set up, setting some states so that things work, doing some additional connections, connecting the buses to the appropriate drivers, and that's the end of that. There are some issues and some additional cleanup that needs to take place. The first I've already talked about is this 4-phase clock needs to be addressed. The second is this clock run mode function needs to be cleaned up as well, because I no longer need the instruction where it ties back to this 4-phase clock and stops on the first cycle, see? And it pauses there until I hit step, and then it goes through all 4 cycles. I no longer need that mode. So I've got run, and then I will have single step, and then this is my single step operation. That'll put the emulator in line with the way that it's going to be built in the future. Number 2, though, is the GUI up here, and that's specifically the simulation window. This needs to be converted into a singleton instance. Well, what is a singleton? If you're not familiar, a singleton means that there can only ever be one object of this class. And no matter how you try to allocate it, either the compiler is going to prevent you from doing it, or you're always going to get a reference back to the already built instance of that particular class. There's only ever one object in the system. And so I need to convert this to be a singleton instance, but I need to do the same thing for my computer class as well to turn that into a singleton instance. Well, why do I need to do something like that? In doing something like that, it eliminates the need for me to have to pass things back and forth between my GUI and my hardware emulator, such as I'm doing down here. I would be able to more easily find the components that are related and make those connections. It's going to simplify the code of the emulator. And so I want to make those changes and make sure that this still works, and then I will come back and demonstrate the final result here. Let me get into that. Okay, as you can see, my clock is in time with my square wave oscillator. I have a 2-mode clock now, as there's no need for that 3rd mode. So I've been able to simplify that as well. So I've got run mode and I've got a single step mode where I can do my single step here independent of the oscillator and then come back into run mode. There is a problem here though, and I'm not going to solve it in this video. I'll tackle that in the next video. And that is that I do not always get a full clock cycle here, and that's going to potentially be a concern in real hardware. So I want to shore that up. I'll do that first thing next video. And then I want to take this and dump this into KiCad and build out the schematic for it, so that I've got a fully functioning clock module that it could potentially turn into PCB. So I at least want to capture the schematic as I've got it here. And we'll walk through kind of a deeper dive as to how I can take the emulator and turn that into a schematic that could potentially then be manufactured. Once again, I've kind of shifted my mindset. I was going to do the emulator from hardware, but I'm actually going to start developing the hardware from the emulator. And as you can see in the background, these connections are going to be how that gets pulled together. So I did a lot of cleanup, and most of what is implemented here is just simply an SR latch, set reset latch, and a button for single step, and a little bit of combinational logic, a couple of AND gates, and an OR gate to get to the actual clock signal. It's very simple logic in the code. I'm not going to do a deep dive into this. The code is available up on GitHub, and I will throw a link in the description and at the bottom of the screen. Next video, I am going to clean up the issue related to short cycle clock, and then I'm going to work on getting KiCad settled out here, at least get the schematic put into KiCad so that I can handle the clock and handle the ALU Adder, because the ALU Adder is complete as well. We'll see you soon.